So I just wanted to run through a quick example of calculating the pH of a buffer using the Henderson-Hasselbalch equation. Now I do have a little example problem here on the screen. And it just basically says, calculate the pH of a 0.15 molar acetic acid solution. Now we can recognize that acetic acid is a weak acid. And then it also says that it's in 0.11 molar sodium acetate. This is going to be a salt, and it does have this common ion, the CH3COO. Notice that these two compounds are essentially only different in one cation. The hydrogen has now been swapped out for a sodium. This is a hallmark of an acidic buffer. Now the Henderson-Hasselbalch equation is the pH equals pKa plus the log of what we're going to call A1 minus over Ha. Now, generically speaking, this anion is going to come from your salt. So that's essentially going to be the concentration of that CH3COO from our salt. And the Ha, of course, is going to be our acid. So that's going to be the concentration of the acetic acid itself. One last little piece of information for this particular problem is that the Ka of acetic acid is 1.8 times 10 to the negative fifth. So at this point, it's now a plug and chug style problem. So if we want to calculate the pH, I would have to take the pKa, that's the negative log of the Ka value, 1.8 times 10 to the negative fifth, plus the log of the salt concentration. Now just be careful because it's really the anion from the salt that you want. And occasionally you're going to have a little subscript 2, maybe even a subscript 3, which means you'll have to double or triple the concentration. Luckily, there's a 1-to-1 ratio here, so I can just straight up use that concentration. So my salt, 0.11, divided by my acid concentration, that's 0.15. And now we're ready to simply plug and chug and find our answer. My mouse is not working. Okay, so let's take the negative log of 1.8 times 10 to the negative fifth, and then add the log of 0.11 divided by 0.15. All right, my final pH comes out to be 4.6. Now, you can still do this problem in a traditional way. You can still actually write out the acid dissociation equation. So that would be the CH3COOH plus water will give you CH3COO1 minus and hydronium. And then find the concentration of that hydronium and take the negative log. The way that you would handle it this way, if you're not going to just use the Henderson-Hasselbalch, you have to drip your concentrations that you know back down into your problem. So my acetic acid was 0.15. That's this chemical. And then the sodium acetate provides the anion acetate in my equilibrium expression. That guy actually would go right here. That concentration is 0.11. We would ice this problem. So again, we don't worry about water, and my hydronium would have to be 0. And then we just start plugging and chugging what we know. We know that the Ka value is 1.8 times 10 to the negative fifth. So there's not going to be any change to either of these initial concentrations, but this one's going to go in as X. So this would be 0.15, 0.11, and X. And now we can actually calculate. So this would be X times 0.11 divided by 0.15. And in this case, my X value turns out to be 0.15 divided by 0.11. I'm coming up with about I'm going to keep an extra sig fig just for fun. 10 to the negative fifth. This should really be 2.5 times 10 to the negative fifth. But remember, we're going to use this to calculate the pH. So I'm just going to take a negative log of that number. And guess what I find when I do that? I find that the pH is 4.6. So it really doesn't matter which method you take, whether or not you're using the Henderson-Hasselbalch, which is a plug and chug, or if you want to do the full ice problem. The thing to recognize is that a buffer has a component on either side of this equilibrium term, and it can resist the changes to pH because there's chemical preloaded on either way that can shift that equilibrium back to where it needs to be.